All right. Okay. Your exams are graded. They should be back to you, hopefully in your hand tomorrow, unless your TAs do something weird again. We got the exam average up, though. 80, almost 3 this time. So right where we wanted, getting us back on track. So you're getting back tomorrow. We'll have a week kind of open regrade submission time. We'll tell you who graded what problems and everything. So you guys state your case, get it to them, just like last time. Saw a lot of awesomely improved scores from exam 1 to exam 2. So hopefully we're back on track. I saw somebody who got a 50 on exam 1 and was 90-something on exam 2. Right? Couple of hundreds, bunch of 99s, bunch of 98s. So life is good. I did see some people slide back a little bit, though. Whoever got that 100 on the first exam only managed a 99. So that trend continues. The final is going to be an 80 or 98, and then who knows what's going to happen, where you go from there. So nice job. You'll get them back tomorrow. The solutions are posted to Canvas. But on to the finish line. Okay, so today we're going to do another look at velocity analysis for rigid bodies. But today's going to be a special case of what we've already done. So when we looked at kind of vector analysis method, remember we talked about last time we got together, we had this vector method. We said, hey, the velocity at point B is equal to the velocity at point A plus the angular velocity of whatever body they're both attached to, crossed with the vector from A to B. So this is our velocity vector approach, and we said this is great if we're looking at just an instant in time. If we wanted something more general over like the entire time path of this, maybe we use differentiation of geometric constraints. But this was our instant in time approach. Today we'll take that a little further and say, this is a nice equation, but what if I can make it a little bit easier? What if there was a special case, if you think of like something that's pinned, here is A and maybe B is out here. What if I could come up with a way to eliminate the velocity of A? And then I just have a single term. I'd have my velocity of B, angular velocity of the body, and then whatever this vector is between them. And all the velocities at this instant in time would look as if they're traveling in a circular path, kind of perpendicular to our pinned location. Wherever you could draw a body. So maybe this is point C, this is point D. Who knows? This idea is going to be called the instantaneous center of velocity. Can we pick a point, even if point A isn't actually pinned? Can we find a moment in time or a position where we can say, hey, point A, as this thing is spinning and flying and tumbling through space, it looks at this very small instant as if A is actually pinned and the whole body's rotating about it. So that's going to be our goal for today. We're going to call that point the instantaneous center, or IC for short. So we'll be able to write our velocity of some point as the velocity at the instantaneous center. So at the center of the rotation, instantaneously, it'll be 0. You're going to have some angular velocity of that body crossed with the vector to point B from the instantaneous center. Now, the goofy part about this instantaneous center, the nice thing is that all these lines are going to be perpendicular to the velocities. But the goofy part is that I might have some velocity of B here. I might have some other velocity of point A here. The instantaneous center for this body may not actually lie on the body. It can be positioned off somewhere else. So I guess the way we could think of it then is that, hey, everything on this body is traveling at this instant in a circular path about this pinned location C. So if I drew another point out here, point D, I would just draw a line back to my instantaneous center. My velocity, perpendicular to that. Another point over here. Draw up a line up. Velocity is perpendicular. So instantaneous center, it looks like pure circular motion about that point for an instant in time. So before you get too excited about this amazing new approach that I'm going to teach you, maybe I shouldn't preface this way. You don't actually need to know this ever, but pay attention. This is just going to be a shortcut technique for solving some vector velocity problems. And what I think it is, it's a nice job of kind of like calibrating your gut or your eyeball so that when you see something, you can say, what's going on here? And try to decipher relatively quickly what's happening in this picture. So it's a little more graphical than what we've used before, is just kind of cranking through our vector equations. So some people like it a little more. Not always helpful, very oftentimes not helpful, but in some cases it can be a nice shortcut. So that's what we'll do today. We'll work on all the different cases where it can actually be used. And some of them are helpful and some of them are not helpful. So there are 3 categories of problems that lend themselves to this technique, and I should probably change that. We're going to talk about 4 today. So we're going to look at 4 different things. But we're always going to use this same idea that if we can locate the instantaneous center, our velocity is going to be perpendicular to that. Well, why is that? Because it's omega cross r. So that's all we need to worry about as we're doing this. So let's look at our 4 different cases and see which ones can be helpful to us. All right. So case 1. If we know the velocity at some point on the body, VA, and we know the angular velocity of the body, we can figure out the location of our instantaneous center. All right, so what we have on the picture here, we've got the velocity of A pointing in some direction. Okay. So the first thing we know about our instantaneous center is it's always going to be located perpendicular to our velocity vectors because we're traveling in a circular path around that point instantaneously. So if I have got my velocity vector here, I can kind of draw a dashed line. My instantaneous center is going to lie somewhere on that line because I have to be making kind of circular motion. So maybe if I try to trick us here and I go opposite way of what's on the screen, if my body's got some rotation, omega, where's my instantaneous center? So the velocity of A is equal to omega of the body crossed with my vector from the instantaneous center to point A. Okay? Maybe now we try to figure out what's going on. Hey, this guy is traveling in a circular path. This omega is rotating. So the thing is like rotating like this, right? So it's traveling about some point down here. The length of this part that I just drew, that's what we're going to solve for. So here I've got some velocity is equal to, I'm not even writing this out again because I'm not going to be able to do anything out of this. So let's pretend like I didn't do that. So what do I know? I know my velocity. I know omega because I'm given that. I know the direction for this vector, but I don't know how long it is. So what we can use is we can use this to solve for the magnitude. And how far away our instantaneous center is from our point. And you think, hey, that doesn't sound that useful. And it's not. Right? I'm saving the best one for last. So if you were able to do this, though, okay, now that I've figured out where my instantaneous center is, maybe I want to figure out the velocity over here at point B. Well, I can write velocity of B is equal to omega cross my r vector for my IC to B, this vector, and have some VB. You think, I'm still not convinced that this is useful, right? Because, hey, if I had this, if I knew velocity and omega, I could have written the velocity of B is equal to the velocity of A plus omega cross the vector between these guys, A and B. All I really would have needed to know was that vector, r from A to B. Yeah, that would have been easier. Case one, great. Let's put it in our back pocket. Probably not going to use that one too often. All right. Case two. Two non-parallel velocity vectors. So I know VA and a VB. And I guess that velocity of A is not parallel. I don't know if that's a legit math symbol. Not parallel to the velocity of B. Okay. So what I like about this one is that I think graphically can help us figure out what's happening. I've got point A. I've got some velocity of A. I got point B. I got some velocity of point B. Locating our instantaneous center. We've got to follow our rules. So let's start with the point we care about, A and B. And our instantaneous center is going to be perpendicular to these velocities because it looks like circular motion. So if I start with A, I know my instantaneous center falls on this line somewhere. If I start with B, I go perpendicular to that. Where these two intersect, that's my instantaneous center. So really, for us, this is the part that I think helps us calibrate what's going on with our eyeball. For instantaneous center, I know that I need to track a line that's perpendicular to the velocity vectors. Where those two things cross, that's my instantaneous center. I can tell you with a lot of confidence that if the structure is a blob like this, and you're given this data, and it's really hard to locate the instantaneous center, like geometrically, like I got to figure out sines and cosines and all this stuff, it's probably not worth it to use it. But if you're given something that looks more like a linkage, and this instantaneous center is very obvious, like, oh, that's actually right at this location, point A, then this is something that can be useful. So here, we know the velocity of A, and we'll write this with respect to our instantaneous center. That's omega AB of our body, cross with the vector from the instantaneous center to A, and B, same thing, omega of the body crossed with the vector from the instantaneous center to B. Now, you know the left-hand side of these, but from this information you can get omega AB. So, in the event that it's very easy to locate the instantaneous center position, this can be somewhat useful in finding your angular velocity of the body. But this is the part that I want you to be able to do. Draw the perpendicular lines and see where it's going. Okay. Slightly more useful now. Case 3. Two parallel velocity vectors with coincident perpendicular lines. So A is parallel to B, and they have coincident perpendicular lines, however you write that out. So what does that mean? Maybe I have a blob that looks like this. These velocities are parallel, so I've got my velocity of A, and I've got my velocity of B. All right, we start at their points. We draw a perpendicular line. And for this case 3, they share that coincident perpendicular line. So if you think back one moment to case 2, we found the location of the instantaneous center by where these perpendicular lines crossed. Here, it's the same line. It happens to just go through both these cases. So the graphical method for locating the instantaneous center, you got to have these magnitudes drawn out to the right sides. This one, VA, is 3 units. VB is 1 unit. Let's just call them meters per second so I don't look like an idiot. And if that's the case, and you've drawn these vectors to length, you connect these two vectors tip to tip, and where that crosses, that's our instantaneous center. Similar to last time, I'm given velocities. If I can figure out the instantaneous center easily, then I can get the angular velocity. So if I'm given the velocity, if it's easy to locate this point, this IC, maybe this is a technique that's useful for finding angular velocity of the body. So this is something we'll see, though, that's a little bit more common. The other case that's drawn on the screen that looks a little different than this, you still got the velocity of A, and B is down here just like before, but instead of pointing to my left, it's pointing to my right. Well, the same is true of the technique. Coincident perpendicular lines. If you have your magnitudes drawn out right, connect these guys tip to tip, and where that intersects, that's our instantaneous center. Remember, same rules apply. I could pick any old point on this thing, draw a line from the instantaneous center. Our velocities are always going to be perpendicular to that, whatever's laying on the body. So where we see this one pretty often is roll without slip. If I've got a wheel that's rolling along the ground, X, Y, Z coordinates. It's got some omega. I want to figure out how omega is related to the velocity at the center of the wheel. So for roll without slip, I might have point Q on the ground here, and right at the edge of my tire, point P. And I'll call the middle O. So for that moment in time, just that instant, P and Q, the tire side and the ground side, aren't moving relative to one another. It's just kind of set right onto it, right? So there's no relative motion between P and Q. So at that instant in time, it appears that P isn't moving. Kind of stopped, right? That's like, do that with your shoes. I did that before, where you're walking along, and I'm walking, my feet are moving, but there's that instant where my heel hits that it's not moving relative to the ground. And that's this idea behind roll without slip. So that tire isn't sliding relative to the ground. So if P isn't sliding relative to the ground, and it looks like this whole tire is pinned about that body, point P is my instantaneous center. It's not going anywhere. So if I wanted to figure out what is my velocity of point O, the velocity of O, my center, is equal to the angular velocity of the wheel crossed with my vector 2O from the IC, or P. So I got VO in the I direction is equal to omega in the K direction, crossed with, from the IC to O, that's this guy. That's my radius in the J direction. I, J, K for my cross product. K crossed with J minus I. So V0 is minus R times omega. The velocity at the center of my wheel is equal to negative the radius times omega. Negative, what happened? No big deal. It's negative because our XYZ coordinate system, positive X moving to the right, positive Z rotation counterclockwise wants me to go to the left. So a little negative sign pops out. It's not too hard. We'll just bring it along. All right, the last one, the useful one. So here I've got A is parallel to B, and we have non-coincident perpendicular lines. Non-C perpendicular lines. I like this one because it's easy. In this case, go back to my blob. Here's A. Here's B. Draw my perpendicular lines through the end of this one. Through B. Hey, A is parallel to B. This guy is parallel to this guy. Then the perpendicular lines are going to be parallel. And there's going to be no intersection point. So if that's the case, and there's no intersection point, these guys have no instantaneous center. Therefore, there's no point in space that looks like these things are rotating around it. Therefore, this body is not rotating. And that is actually useful. So if you can look at an object, immediately identify that it's not rotating, then you've got that the velocity of A is equal to the velocity of B on that body, which is equal to the velocity of anywhere. Pew, 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 pew. They all have the same velocity. And also, if I give you this drawing, it looks like this. The velocity of A. Over here, the velocity of B is real little. And you say, hey, I'm going to draw these perpendicular lines. But the velocity of A doesn't equal the velocity of B. I can draw whatever I want. Doesn't mean it actually works, right? This, not physical. Or elastic. It's not rigid. In order to make this configuration work, it's not a rigid body, and all these equations that we've been talking about don't apply to it. So maybe you can just identify easily that that condition that I just tried to throw at you doesn't work. So this is the one that I think is useful. I think we'll do an example maybe in discussion tomorrow. Oh, actually, we'll do an example right now that shows how life can be quick and easy if we've got a problem that we can easily identify as not rotating. It's our old friend. All right, so we looked at this problem last time we got together, and the first thing I did was I flipped omega AB. And what did we do? We knew the velocity at C here. It's given in the problem, 4 feet per second. We knew A is pinned over on the other end. And we used B as this go-between between our mechanisms. Hey, I'm going to write equations about what's happening on the velocity, rigid body velocity from BC. I'm going to write that same equation similar from AB side. And then where they meet, that's point B, and they better share that same velocity because it's pinned there. But now, we're so super smart that we know what this looks like. And we could say, hey, if this rigid body has a velocity coming down, and B is traveling in a circular path, so its velocity is up or down. Maybe I can't tell. I'm not good at reading these mechanisms. I don't know what way B is going. Well, this can maybe tell us a little bit about it, right? So I can see the velocity of C, use my rules. I draw a perpendicular line, looking for my IC. Has to lay on that. And then I do the same thing for B, and I say, hey, perpendicular line. What I've got are parallel velocities going in different directions that do not share a coincident perpendicular lines. So, right away, my velocity of B is equal to my velocity of C. And I can say that, it's going down because C is going down. So, very quickly, examining what's happening here, using the one rule that's actually kind of useful, the fact that this body isn't rotating, we can jump in here and immediately know what's going on. Okay, my velocity at B is the same as my velocity at C, so at this instant in time, this bar that's angled like this is purely translating. It's going straight up and down, but only for that instant in time. And then if I want to figure out the velocity of A, it's just one little step away. The velocity of A then is omega AB crossed with the vector. I screwed this up. My velocity of B is equal to omega AB crossed with the vector from A to B. If we wanted, we could have snuck in here a velocity of A as well, but that is pinned. So velocity of A plus that. So before, where we had to take equations from one side, equations from the other side, say what we know, meet them in the middle, they had to be equal. Now we're clever. We can just look at this thing and say, not rotating, one line, we're done. Problem solved. So the one thing this problem is good for, obviously showing you the utility, how this makes problems easier, but also thinking about how this instantaneous center isn't just a point that's always in the same location. It's only valid for that instant in time, and it travels all over the place. So let's look at where it goes. So for the case drawn, we just told you no instantaneous center. I'm going to pretend that A is a disk instead of just a little bar. Everything travels around it. I've got B out here, and maybe I've got C up here. So C travels just up and down. It's stuck in that channel. So if C is going up and down, my vector from A to B, B is traveling in a circular path. Its velocity is perpendicular to the circle. If I want to find my instantaneous center for this thing, imagine this is a channel, follow our rules here. I draw a line perpendicular to B. That one's pretty easy to draw because I got an A pinned. A line going through C and perpendicular. There's my instantaneous center, way out in no man's land. If this was aligned slightly differently, maybe it was like this. B and C are all lined up. Okay? I got my velocity of B. Perpendicular to that, dashed line following our radial direction. Then I go to C and I look perpendicular to C. Hey, point C is my instantaneous center. So as this thing is rotated up, my instantaneous center, maybe I should have done this too. We've got a bar going here. That bar BC, same as this bar. My instantaneous center is kind of walking. At the position where this bar AB was horizontal, like what we have in the figure, instantaneous center didn't exist at all. I start rotating up. Hey, it pops up, but it's way over here. As this thing rotates a little further, the instantaneous center comes into a line with C. As it went further, it would keep kind of going over. So it is instantaneous. It only is valid for that one configuration that you can draw. Don't try to use it in general. And that's what makes this technique pretty much useless if you're trying to use instantaneous center for an object and you're trying to define its velocity over a whole range of times. Because you're trying to track this instantaneous center all over the place then, and life becomes very difficult. All right, last example. We have the angular velocity of link AB going at 4 radians per second. That is our guy down here. A is pinned, by the way. Determine the velocity of the collar at C and the angular velocity of link CB at the instant theta equals 60. So what's shown here? So we want to find omega CB or BC, and we want to figure out what's happening here with my velocity of C. Use the instantaneous center approach. Okay. So first off, you don't need to use instantaneous center approach if you don't want to. And maybe we'll just like quickly talk through that so you can see where it would go. Hey, I'm trying to figure out the velocity of C in this angular velocity. How would I do that? I would start over here at A, and I would figure out the velocity of B as omega AB cross the r vector between them. And then I could write the velocity of B again for the other body. And that's with respect to the velocity of C and its rigid body, omega BC. So if you wrote these two equations, you'd actually be able to solve this. Pretty much right away, as long as you can write this position vector RAB, you can find the velocity of B. Check. Move one equation down. All right, what do I don't know now? I don't know this, and I don't know my angle. No problem. That's essentially three unknowns, because velocity of C has an x and a y component. Angular velocity, it's a third unknown. And from this equation, you've got an x and y, or r and theta, whatever coordinate system you've picked. So you don't have quite enough information until you realize that we know the direction for VC. It's got to go along this slider. Its magnitude is the only thing we've got to figure out, because it's constrained motion to move at the 45 degree. So whatever its x component is equal to its y component. So this is really two equations, two unknowns, once we get to this point, and you can solve it. That's how I would do it if I wasn't giving a lecture on instantaneous center. But how are we going to do it with IC approach? I've got C here. We'll use that same idea. Maybe we'll throw that in our back pocket. V of C is at a 45 degree angle. So VCX in the I plus VCY in the J. And we know that those two things have to be equal. I don't think I need to use this for this approach, but I already said it, so I might as well write it down. This bar BC comes out horizontally. This is 45 degrees down to point A, which is 60 degrees. Okay. So we're going to try to do this with the instantaneous center approach and kind of think through things. I can get the velocity of B pretty easily because I'm given omega AB, right? So I'll know what this looks like and solve it pretty simply. But then I want to figure out what the angular velocity of CB is, so we can figure out the velocity of C. So that's what we're going to use the instantaneous center approach for. So maybe step one. How do we find our instantaneous center? Well, I kind of already started it. Maybe a bad drawing, but velocity of B, because A is pinned, it's moving in a circular line, a circular arc around A. So my instantaneous center lies somewhere along that line. Velocity of C, my eyeball can't tell if it's going up or down. But I've got its point, and I can draw a line perpendicular to that. So there, on this bar, is my instantaneous center. It's some goofy angle and some strange portion down the hill, but we know what line it lies in, so we're not totally empty here. So a little geometry. This here is horizontal. This guy, BC, is horizontal. So this angle is equal to this angle, these two interiors. That's 60. I jump up to C, and C is at a 45 degree relative to the horizontal. So its complementary angle here is also 45 degrees. Then the last bit, triangle. Angle plus angle plus angle equals 180. 75 degrees. Okay, there's the last one left. I'm going to call this length B over here. This can be length A on this side. And our figure tells us this is 35 millimeters, or 0.35 meters along the top. So we got 0.35, B, A, 45, 60, 75. I can figure out these lengths with the law of sines. So 0.35 meters over the sine of its angle opposite is equal to B times the sine of the angle opposite of that one, which is equal to A over the sine of the angle opposite of that, which is 60. So, law of sines to get A and B. A is equal to 0.314 meters. B is equal to 0.256 meters. So we've located how far they are. Okay. All right. So we know how far down our instantaneous center is, because we just found what B is. We can figure out the angular velocity of BC based off of our instantaneous center, because we know at this moment in time, as BC's moving this way, it looks as if every point on that body is rotating about my instantaneous center for this body. So in order for us to do that, I guess maybe first we should find the velocity of B. So maybe step 2. The velocity of B from AB is equal to the velocity of A, just writing that for fun, we know it's 0, plus omega AB crossed with R from A to B. All right, my brain looks at this, I see it in an XY system, and immediately I think, I'm going to break this up into its XY coordinates and solve for a velocity of B in that direction. You can do that, or you could leave this thing in polar and say that, hey, in polar coordinates, this is my R direction, my velocity is in the theta direction, and I can find my velocity in that theta direction. We could use that with the, hey, velocity in the theta direction for my IC, still the same direction, and I could figure out omega BC really easily. But we'll do it the hard way. So my velocity of B this way, velocity of B is omega AB in the K, which we've got as 4 radians per second, crossed with my vector from A to B, that's 500 millimeters, or 0.5 meters, times its x and y components. So this is the vector I'm trying to figure out, A to B. Can break that into its x and y pieces. Cosine 60 degrees I plus sine 60 J. Okay? So I've got 4 times a half, I get 2. My velocity of B, 4 times a half, I get 2, is minus 2 sine 60 degrees in the I plus 2 cosine 60 degrees in the J. I skipped the cross product. You guys can do that. All right, so we've got the velocity of B. Now if I jump back to my triangle to show what we got here. Here's my instantaneous center. Here I just solved for velocity of B. I can figure out the velocity at any point on this line if I know what the angular velocity of this body is relative to the IC. So, step 3, find the velocity or angular velocity of BC. And I can do that with my velocity of B is equal to the angular velocity of BC crossed with the vector to my IC. R from instantaneous center to B. So the velocity of B, I can plug that in. Minus 2 sine 60 degrees I plus 2 cosine 60 degrees J is equal to omega BC in the K direction crossed with this vector. Hey, we got that. We told you its length is B, so 0.256 meters. And its direction, cos 60I sine 60J. I've got 2 equations. I can look at the I's, or I can look at the J's. Doesn't matter. You pick, you get the same answer. Ooh, this is 7.8 radians per second. So I can use the I equation or the J equation. Doesn't matter. Last step. Find the velocity of C. So we already got our instantaneous center located. We know what our angular velocity of this body is. We could say the velocity of C is equal to omega BC crossed with the vector from the instantaneous center to C. Or we could say that the velocity of C is equal to the velocity of B plus omega BC cross the vector between those two. And you take a look at these, and why might I use one or the other? Well, this first one, less terms. I like that. But a little bit of a pain in the butt to write my vector from the IC back to C. The second one, more terms, a little trickier, but I've got a nice expression for the velocity of B, and my vector from B to C is a horizontal line, super easy to write. So this one might actually be a little easier. Either way, we get that the velocity of c minus 1.73 in the I, and it has to be the same in the j because of the way it's traveling. All right, that is all. I'll see you guys on Thursday.